So welcome back, everybody. The topic this week, and also parts of next week when we will meet in person again, is to try to wrap up this discussion of deep learning methods. And today we're going to have an emphasis on convolution neural networks. And next week, we will also follow this up with a discussion of recurrent neural networks. And we will also try to wrap it up with some applications of so-called general adversarial neural networks, or GANs as they're called. But the aim today is more to give you some of the basics of a convolution neural network. Then after next week, so that will be on March the 14th, the idea is to start with a new topic, which could be, and I've already received some feedback from some of you, that Bayesian statistics combined with Gaussian processes is something which could be of interest for the final part. You know, as I mentioned a little bit earlier, some of you are also more interested in a direction which goes into differential equations. So clearly we, when we meet then on March the 7th, next Monday, we should try to discuss possible paths which are more tailored to your own research interests. So but the topic today is to try to wrap up this part of convolution neural networks, which we started with last week. I just wanted to quickly remind you of basically where you find the videos and the material from the lectures. So if you scroll down here, you will find a video of the lectures with also subtitles from last week, and at the same time the handwritten notes. And if you go a little bit more up here and click to the link on the right here, you get straight into the lecture slide material which we have. So the topic this week is about essentially convolution neural networks. And when we're done with that, we're going to move into the topic of recurrent neural networks, which are also widely used in machine learning and deep learning approaches. But let's remind ourselves a little bit about the topics and the kind of material which you can download. So there are some videos here. If you come across some interesting videos, please do let me know, and I will just list them and share them with all of you. There are some resources at the University of Oslo. There's a course called IN 5400, which is actually a course on image recognition and machine learning, and it has actually an emphasis on convolution neural networks and deep learning methods tailored to image recognition. So if this is a topic for your research, I would normally strongly recommend to try to follow this course here, or just look up the lecture notes, because the lecture notes are available online. The typical reading recommendation which I give when it comes to deep learning is a text by Goodfellow, which probably is the best text in the market. And they do not go so much into the mathematical details, but they explain very well how you would actually build up a convolution neural network. We are going to link this with the way we would encode it using Tensorflow. So as we said last week, we went through some of the basics of a convolution neural networks, and they were developed during the last decade of the previous century, but they never took off before, let's say, 2010, 2011. And since then, they've been actually the standard methods for image recognition. And you have a huge data sets which are used in the training of image recognitions. So if you're looking at face recognition, there are millions and millions of human faces which enter the training of a convolution neural network, which is tailored to facial recognition, and so on and so on. So you have a huge database like ImageNet, which has been used to train convolution neural networks. Now, the thing which we discussed a little bit about last time, we just mentioned some of the basics, is that the CNN architectures, they often are tailored to specific types of inputs. And they are to a very large extent, tailored to images. So there are specific features with images. If you're looking at the house, as we discussed last week, you would have the corners, you would have the windows, the doors. You would pay less attention to reproduce the color of the house, because that's something which would be pretty common to a large fraction of the house. But you would tailor it more. When you look at the image recognition, you would tailor it to specific features. So that means that there is some kind of filtering. And this filtering is something which is very common for the field of image recognition. So the standard field of image recognition has used filters like so-called Kalman filters. Fourier transforms have been widely used in imaging and signal treatment. And these are all kinds of operations which have a kind of commonality, which we normally call convolution in mathematics. And thereof the name convolutional neural networks. A neural network, as we have been discussing, is normally something which we will call an affine transformation. So a vector is received as input, or it could be a matrix. It's multiplied with a matrix of the so-called weights, and that produces an output. And these operations involve the full and dense matrices and vectors. And what we are doing with convolutional networks is actually try to reduce this dimensionality. So one kind of overarching take you could have on convolutional neural networks is that you could think of them as an efficient way of performing a dimensionality reduction. So these are slides which we went through a little bit last time, and I'm not going to repeat them. But you can see now that if you were to run, and this is just a quick repeat from what we did last week, if you wanted to perform a image recognition on an image of a size which has 32 pixels times 32 pixels, which we normally would call 32 wide and 32 high, with 3 color channels, it means that you would need something like, just for one single fully connected neuron, you will need something like 3072 weights. And if you want to increase this to an image of a more respectable size, 200 times 200, it leads to quite many weights for just one single neuron. So since you have many such neurons in a hidden layer, it means that your dimensionality would increase dramatically. So if you have 100 hidden neurons, this means just for that specific layer, that you would have more than 1 million weights to determine in a backpropagation algorithm. So this is this kind of full connectivity quickly exceeds what you would like to deal with computationally. And that's where the idea behind convolution neural networks actually comes in. So they normally take advantage of the fact that the input consists of images, and they constrain the architecture in a more sensible way. As we said, if you're looking at houses, you are typically looking after corners, windows, doors. If you're looking after human faces, I mean, you're looking after a mouth, eyes, nose, and these are features which are pretty common to a human face. If you're looking after, let's say, recognizing specific animals, they have some specific features which you can use to train the neural network on. So the typical setup of a neural network within the convolutional neural networks consists now of different types of stages. And the typical stages, the most common one is obviously you have some kind of input layer. And these convolutional neural networks can actually be pretty complicated and very, very deep. And it has 3 types of elements which normally define the so-called convolution process. So these are the convolutional layer, where you perform the mathematical operation of convolution. This convolutional layer produces an output, which is then filtered through a activation function, and it has a pooling layer where you can actually perform a further downstreaming of the data. And we are going to discuss these three different operations, because these three operations, when you take the convolutional, the ReLU, and the pooling part, they normally define what is called a convolutional stage. And then you can do something which is called a fully connected layer, which normally compute class scores, resulting in volume of size much smaller. And you can actually connect this downsizing of the data. So through the convolution down to the pooling layer, you can think of this as a way to downsize the size of the problem. Then if you have downsized the size of the problem, you could send it through a new convolutional layer, or you can actually run it through a standard neural network layer or a series of neural network layers. So they transform the original image layer by layer, and some of the layers contains parameters and some do not. The convolutional layer normally contains parameters where you would apply the gradient descent. The ReLU and the pooling layers, they are normally not including any types of parameters, except that you can think obviously of the usage of a activation function as a type of parameter. The pooling part also has a way to set up the kind of reduction of the dimensionality, which also involves a fixed parameter. So when we look at these ReLU and pooling layers, we normally think of that as a fixed operation, which you would change afterwards. Whereas the typical training, which is done by the backpropagation algorithm, is normally done in what we call the convolutional part, or the convolution part of the operation. So we are coming back to these things. So if we now go and look at the mathematical ideas, I just wanted to use the slides a little bit, and then we are going back to the whiteboard just to slow down the pace a little bit. So a dense neural network is represented, as we said, by an affine operation, like a matrix vector multiplication. And the key idea in a CNN is actually to only keep the information from the neighboring pixels to be related. So we collect only neighboring neurons in the input instead of connecting all with the first hidden layer. And this is normally done by the mathematical operation of convolution. So if you want to think of convolution, you could think of it in the following way. So it's a kind of filtering. And in the mathematical operation of convolution, you operate on two types of functions to produce a third function that expresses how the shape of one of them gets modified by the other. So convolution has a plethora of applications in a variety of disciplines, and that spans from statistics to signal processing. You have computer vision, solutions of differential equations, linear algebra, and actually machine learning here. So if you think back of a convolutional process, mathematically, it's actually expresses by this. So you have some kind of input data, and in imaging, this function W, which we would typically call a weight function. So the way you could think of this now is that this X of A represents some kind of measurement you're making. Suppose this is a car which is moving as a function of time, and you measure the positions of the car as a function of time, X, but then your measurement data may be a little bit noisy in the beginning, and you want to filter out the noise by having some appropriate weight function. So this weight function, which you would define here, is often also called a filter. And in imaging and signal processing, this is this kind of operation which you see here is a pretty common operation. So the filter then is something you would adapt to the specific problem. So mathematically here, what this could represent, if you're now measuring the position of a car as a function of time, and in the beginning, there is a lot of noise, and then your measurements get calibrated properly and noise gets reduced. So you could put emphasis on, let's say, a later time t here, and then you would integrate away all the other ones, and you would end up with a final output y of t, which has now been run through this weight function or this filtering. So just let me know if this is something which rings a bell, if this is familiar. And mathematically, you would often write this operation in a more compact way. So the convolution of x with w is not given by this operation with the asterisk here. You can do the discretized version of this kind of filtering by now running over all the discrete measurements which you have, which would be the normal situation. Actually, you would have a discrete set of measurements, and then you would simply run it through this weight function or filter function. And this is the idea. Now, in a convolutional neural network, the setup of this weight function, that is the setup which then enters the backpropagation algorithm, so that you can actually obtain the best possible way to filter the relevant information. So you can now think of this filtering here as being, or weight function, as being a function which is then adjusted, or the parameters of this function is now being adjusted by the backpropagation algorithm in the convolutional stage. So if you do the inverse, that is normally called a deconvolution. And these are mathematical operations which are, you can just go back from a deconvolution to where you started, because you know what the operations are. So there are some simple operations which illustrate this. And one of them, which I wanted to show you, is the, like when you met in project 1, we tried to set up a design matrix for two-dimensional function. And that was an example of a polynomial multiplication, which we did. You can actually recast that operation in terms of convolution. So I just wanted to remind you of some specific ways by which you would do convolution and how you can represent specific mathematical operations. So suppose you want to multiply two polynomials. And this is a little bit reminiscent of what we did in project number 1, where we had a function we wanted to fit within terms of a two-dimensional function. And in that case, we had a polynomial in x and y. So you could now think of two polynomials which are multiplied. So you have a second order polynomial, and then we have a third order polynomial, which means that the final polynomial is a polynomial of degree 5. Now, in our case then, the final polynomial contains now these parameters, delta 0, delta 1, delta 2, and so forth. And we can set this up in a very efficient way in the following way. So this is a pretty simple example. So we know then that when we perform the multiplications here, we would get an alpha 0, beta 0, alpha 1, beta 0. Oh, this should be, sorry, this is a typo here. Let me just take note of that. This should be an alpha 0 times beta 1. So this is actually a small typo here. I didn't notice that before now. And then if I look at the other coefficients here, they will now contain different admixtures of these parameters, alpha and beta. So you notice that alpha runs from I equals 0 and 1, and beta from 0 to 3. So that means that you could, if you want to write this out in a brute force way, the mathematical process of this discrete convolution would simply be alpha I, beta j minus 1. And the advantage of doing this, if you think of you performing a brute force polynomial multiplication, where you multiply this polynomial with this polynomial, which would be very inefficient, is actually that you now can take these coefficients which are looking after, and you know the degree of the polynomial, and you can simply limit these operations now to those values which are non-zero. And mathematically, you would actually rewrite this operation here in terms of what we would call a convolution, a discrete convolution here. And it's pretty easy to see that you can actually do that. And clearly, when you do this, there's a drawback here because we are summing over I and j going from minus infinity to plus infinity. But we would clearly limit this to the operations which are available. So we would define I to be non-zero for only some specific values here. So you can now, since we only have a finite number of these alpha and beta values, which are non-zero, you can rewrite this operation here as a matrix vector multiplication. And you could simplify it like this. And this is normally something you can run pretty fast, also because the matrices are normally sparse. Or since the process is commutative, you can easily see that you can rewrite the multiplication in terms of a matrix holding beta and a vector holding alpha. So this is actually, if you think of the commutative process, you can actually rewrite it in a much simpler way. And this is a matrix times a vector, which requires less floating point operations. So when you use these matrices for mathematical purposes only, and these are not set up for an implementation, when you implement the above equation, you do not encode or allocate memory for the matrices explicitly. You would rather code the convolutions in the minimal memory footprint that they actually require. So in this typical case, what you would do then is to simply set up the minimal parts which are needed. But you see now the way you would do this, and you could think of these operations as something which is run through a filter. So you have rewritten the polynomial multiplications in terms of a more efficient algorithm. And I invite you to take a look at the number of floating point operations which will be involved if you now use this more compact expression which you see here, and you simply run over those elements which are non-zero. Okay, you have other examples, and I'm not going to go through that. Another example of a type of convolutional process, which is in a sense represented by a Fourier transform. So a Fourier transform in a certain way is actually a way to filter out information. So if you're familiar with the theory of Fourier transforms, you could just take a look at the slides here and remind yourself a little bit about the mathematical operations which are done in terms of Fourier transforms. So I'm not going to go through that one, but there are some simple examples here on how you can actually run the calculation with Fourier transforms. Now, if you now go to the mathematical operations, which is done in a convolutional neural network, you have a typical, if you now have a two-dimensional image, and this image is I, this is the image which you're inputting. You could now have a filter which is defined by normally what we would call a kernel, K. And this would lead to some output when we now write the mathematical operation here, where now the filter actually has a much smaller dimensionality than the matrix which holds the information about the image. So by this kind of process here, we're actually now producing an output which has a smaller dimensionality than the one we started with. So convolution, as I said, is a commutative process, which means that you can actually rewrite these equations in terms of the opposite process. And normally the latter, which you see here, is more straightforward to implement in a machine learning library, since there's less variation in the range of the values of n and n. Because the filter is normally a much smaller object than the matrices which we are inputting. And if you go back to that simple example of the matrix, no, the polynomial multiplication. So if we go quickly back to what we saw there, let me just show you again the difference between, so it's a commutative process. So we could set it up as the matrix which represents the alpha parameters, and the matrix which represents or the vector in that case, which represents beta. But since it's a commutative process, we can actually rewrite it in terms of a matrix holding beta and a vector which is holding the alphas. This is the, how to say, the essential mathematics which takes place in the process of convolution. Now, when you perform these operations, there will be weights, which now are going to find the optimal types of filters. And these weights are those parameters which are defined by the backpropagation algorithm. So the most standard way of doing this is something which helps. I see I have some typos here. This should be actually J plus N here. So I have to, let me just take a note of this because I see that there are some typos here. Let me correct that right after we've done with the lecture today. Let me just take a note of the typos which we have here. Okay, sorry for these typos. This should actually be a plus N here. Now, if you now look at the dimensionalities, if you look at the fields like signal processing, one designs normally so-called filters, and these filters are defined by the convolutions, and often, and you will be surprised to see how much they are handcrafted, and it will depend very much on the type of signal which you're expecting. And if you're, as I mentioned earlier, if you're trying to reproduce images of houses, these are normally really handcrafted to the detection of properties of houses. So you would have you may specify filters for smoothing, edge detection. You can have a frequency reshaping and similar operations. However, with neural networks, the idea is to automatically learn the filters and use many of them in conjunction with nonlinear operations, which are the activation functions. So that is the next step in a convolutional layer. So you have the convolution process itself that produces an output, and that enters a nonlinear function, which is typically your activation function. It could be the sigmoid, it could be the Rayleigh function, and other types of functions. Now, if you now take the neural network operation on a sequence of, let's say, sound data, so you can assume that you have an input vector, which has a length of 10 to the 6th, and then you construct a neural network with only one hidden layer with 10 to the 4th nodes. That means that you will have a weight matrix with 10 to the 10th weights to be determined, together with 10 to the 4th biases. So if you assume that you have one output layer, which is meant to train whether the sound sequence represents a human voice or something else, which will be false, so you have simply a binary output, it means that we have only one output node. But since this output node connects to 10 to the 4th nodes in the hidden layer, there is in total 10 to the 4th weights to be determined. So that means that the number of parameters here is of the order of 10 billions. And this is a pretty sizable problem. And to be able to reduce that type of problem is what the convolutional neural networks actually offer as a solution here. So in today's architecture, you can train such neural networks. However, it's a huge number of parameters for the task at hand. And in general, it is very wasteful and inefficient use of dense matrices as parameters. And just as importantly, such trained network parameters are very specific for the type of input data on which they were trained. So it's not likely that this type of approach will generalize easily to variations in the input. So if you have another type of image, you would actually have to redo everything. And the main principle that justifies convolution is locality of information and repetition of patterns within the signal. And sound samples of the input in adjacent spots are much more likely to affect each other than those are far away. If you're looking again at this example with houses, you would have windows, and the windows would normally not affect the color of the house. So you don't need to encode all the information about the colors of the house. Sounds are repeated in multiple times in a signal. While slightly simplistic, reasoning about such sound examples demonstrates the kind of ideas behind a convolutional neural network. And this same principle applies to images because you have specific features you can train your network on. And this data set, which is called ImageNet, which is a huge collection of images, is an example of a convolutional neural network which has actually been trained to this. So what I wanted now to go through are some of the basic properties of a convolutional neural network. So let's try to do that now. And then we are going to go back to the examples and how we can do this using TensorFlow. So I'm just going to switch back to the whiteboard. So let me just change a little bit here. I just need to get up my notes as well. So let me bring up my. So if we now look at the CNN, the first stage is the so-called convolution stage. So if you're setting up a CNN here, the normal CNN will then contain something like this. There would be an input layer, as before. So that defines the type of image which we have. And that could contain some images with a given number of pixels and colors. This feeds in to what is normally called the convolutional operation, or the basic convolutional stage. So I'm just going to write this as a conv stage. Some people call this a convolutional layer. So this contains the convolution itself, and after we've done the convolution, what we would have then is something which we would call a detection stage. So this is normally called a convolution stage. So the whole convolutional layer consists of normally 3 types of steps. So this is called the detection stage. And normally that involves the application of the input from the convolution stage. So you can think of this convolution stage as producing an output. This is now fed into the detection stage. So this goes in here. And then the detection stage feeds in to the last stage, which is normally called a pooling stage, which is a further dimensionality reduction here. So this is the pooling stage. Or people mix sometimes the naming. So people will call it the pooling layer, the detection layer, and the convolutional layer. But the whole convolution process or convolutional layer consists normally of these 3 types of operations. Then we have something which is called a flattening stage, which we're coming back to. But the next thing here is that this could now be fed into a next type of processing of the data, which could be, for instance, a standard neural network. So this could be a standard feed-forward neural network, because then you have reduced the dimensionality of the problem so that you actually have something which can be dealt with a standard feed-forward neural network, or you could have more complicated convolutional processes, or more, I'm just going to write convolutional layers. So that means a further repetition of the stages which I've seen here. And this ends up in this so-called output layer here. And that's where we would then compare with the final data, and where we set up the metrics and the loss function. Data, and assess the quality of your model, and assess quality of model. Via some metrics which you have, and the typical metrics is normally defined by the cost function, and assess the quality of model via normally what we call the cost or the risk or the loss function, risk or error, etc. function. So let's now take a look at what these three basic elements in a convolutional neural network actually mean for us from a operational point of view. Sorry for that. So let's look at the convolution itself. So now what we're going to do now is to go back to the basic operation. So this is normally called the convolutional layer. So with a convolution stage, a detection stage, and a pooling stage. And let's see how we can actually reduce the dimensionality here now. So suppose you have an input. So this is the convolution stage. So we have some input. And let's write this as a kind of matrix. So we would now have a matrix here. Let's just rewrite it in terms of different boxes, which have different types of inputs. So suppose this is the exciting input matrix. So this is now a 3 times 4 matrix, C and D, and then we have an E. This is just me testing that I actually do know the alphabet, I, J, K, and L. So this is my input. And then I have some kernel here, or filter. It's often called a kernel, but you will also encounter this depends on the different types of fields. If you're going into imaging or signal treatment, people would normally call it a filter. So suppose this filter is just a 2 by 2 matrix. And it looks like this. Of X and Y and Z here. Now, one thing you can define is something which is called a stride. This is a parameter when you're setting up the convolution process. So what I'm going to do now is to do something which is called stride equal to 1. So what does that mean? Now that means now that when you look at the filter, I'm now going to go through in the first step, I'm going to look at this object here. So I'm doing an operation here, which is the convolutional operation. So this process here means now that if I do convolution here, I'm multiplying A with W plus B times X plus E times Y plus F times Z. So that would be the first operation I'm doing. Now, stride 1 means that the next operation which I'm going to do is an operation where I'm going to move just one step here from A to B. So I can make a larger stride. So this stride becomes a parameter. So my next operation now is given by the following content. So I have a B times W plus a C times X plus F times Y plus then the final one, which would be G times Z. Now, since I'm having a stride of 1, it means obviously that my next operation has to be given by this box here, which is now filtered through the kernel. So I would get the next operation here, which now gives me C. If we now bring it up here, we have a C times W plus a D times X plus a G times Y plus an H times Z here. Now the next operation, since the stride is equal to 1, means that I have the brown box here, which is this box. And then it proceeds with the 2 more boxes. So what I would get then, if I do the brown box, so I'm actually reducing the dimensionality from a matrix which was 3 times 4. So if you look at this matrix, it's a 3 times 4. I have a filter which is a 2 by 2 here. And as you can see now, I'm reducing this to a matrix which is actually 2 times 6. So the way I'm going to do the filtering now is something which has the potential to actually reduce the dimensionality of the problem here. So the next layer is now given by an E times W plus an F times X plus an I times Y plus a J times Z. And then it just goes on. And if I do the next one with my stride equal to 1 here, this is the next box. So that is going to give us F times W plus G times X plus F times Y plus K times Z. And finally, I have the last box, which now is given by the final color here. So I would have this box here, which now contains simply G times W plus H times X plus K times Y plus L times Z. So I perform the filtering of the data now. And normally what I want is that the dimensionality of this matrix K, which I have here. So we want normally the dimensionality of K to be much smaller in general than the input. So when I'm writing it like this, I'm thinking of the dimensionality of the matrix K with respect to the matrix I. Now, when you do this operation here, what happens is that the way you set up the filter, the optimal type of filter, is something which you can adjust using the backpropagation algorithm. So the filter size and the way you perform the filtering is normally left as a parameter in the optimization process. So the filter size. Now, I should also say that what we are doing now when we look at convolutional neural network is more to take a kind of overarching view. So we are not going into the gritty nitty details, which are then pretty explicit for a specific, let's say, problem. So if you're filtering some kind of signals, the way you would set up this kernel or filter is something which would be pertinent to the type of problem which you have at hand. So the filter parameters, so that's the size of the filter. It means also the ways you perform the operations. So the filter parameters are tuned by the CNN. So these are the parameters which you then would tune in something like the backpropagation algorithm. Now, when you have this now, this filtering process, so this convolution of I times K, so I'm just writing this as a convolutional process, produces an output. And this output goes into, which goes into the detection stage, which is the same, and I'm just putting this as an equality with an equality sign here, which is the same as the application of a so-called activation function of a user-chosen activation function. And this type of activation function is typically chosen as, so typical examples of these activation functions are, for instance, the ReLU function, which is widely used. It's very simple to use, and that produces a specific output here. So the typical activation is a ReLU or any of the kind of linear units, exponential linear units, or ELU, or similar functions, because they are pretty easy to implement. So this is something which is fixed by you, but you can obviously think of this as a kind of parameter. And many people would then play around with different types of activation functions. But when you run the neural network, the convolution neural network, the parameters which it would be fitting would be the weights which are involved with a filter which you have chosen. And you would then keep that as it stands. So the next thing is that this is fed into a so-called pooling stage. And this is what we will discuss after the break. So unless you have any specific questions here, I would propose that we take a small break. I'm going to pause the recording. Try to run it. So the thing which I wanted to discuss a little bit now are some of the elements which are included in the setup of a convolutional neural network. So we looked at the so-called convolutional layer, which contains a convolution stage, and that's where we get parameters we need to train. Then there is a detection stage, which actually contains the output from the convolution stage. So this would just be a linear output. So you have a matrix or times a vector, for instance, that produces a linear output. Or you could think of this convolutional stage. And then this is fed into some type of non-linear function, which in our case could be a standard activation function like a sigmoid. It could be a rectified linear unit. It could be an exponential linear unit, or any of the other activation functions which we have met. This produces a new output, which is then sent into the pooling stage, which is a further way of reducing the dimensionality of the problem. So the detection stage and the pooling stage, in a certain sense, they don't have parameters because you have fixed these upon the setup of the convolutional neural network. But let's look at some of the items which are important when we are setting up a convolutional neural network. So one of these is something which is called a sparse connectivity. So this applies now to the convolutional stage. So what does that mean? Now think back to a standard feed-forward neural network. And suppose that we have only 5 nodes, 5 input nodes, and then we have the 5 output nodes. So when I say FFNN, that's normally a feed-forward dense neural network. So this would be a dense neural network. And suppose now that you have 5 input nodes. So let's call this X1, X2, X3, X4, and X5. And then we have the hidden nodes here. So let's call this an S1, S2, S3, S4, and S5. And in a standard feed-forward neural network, what happens then is that S1 receives an input from X1, but it receives also an input from X2. It receives an input from X3. It receives an input from X4, and it also receives an input from X5. Now, the same thing repeats itself with S2. So this is a fully connected neural network. So it receives an input from X1, from X2, X3, X4, and X5. Similarly, we have for S3 receives an input from X1, X2, X3, X4, and X5. And then I'm just putting dots here and etc. So this is the typical setup of a feed-forward neural network. In this specific case, what we need then is something like 5. So we have 5 inputs times 5 weights to train. Now, when we do a standard convolution neural network, what we often have then is a much sparser connectivity. So it means that what we could have, and let's just put up the CNN, and we're going to write down the same nodes. So we have an S1, an S2, S3, S4, and S5. So you can then decide the size of the connectivity here. And you could now think that there are only some specific properties which now feed into a specific hidden node. So what you could think of now is that there are only 3 of the input nodes which connect to one of the hidden layers. So you could now think of X1 connecting to S1, X2, and then X3. Similarly, now you could reduce the inputs to S2 to only X1, X2, and X3. So what you could have now is something like this. And then from that, then further on, when we now move to S3, it gets only an input from X2, X3, and X4. If we now look at the S4, that receives an input from X3, X4, and X5. So obviously we would have points which come from here and which come to the left. It depends on how much we have to the right and to the left. So some of the points may only receive inputs from 2, that would be the outer points. And then all the inner points would receive a connectivity which links it only to 3 input nodes. So if you look at the S3 from above, so if you view that from above, what happens then is that you now have, if you look at S3, that would have an input from X2, X3, and X4. And then we have an S3 here, which now is only receiving an input, instead of receiving an input from all the input layers, input nodes, it receives an input only from 3 of them. So in this specific case, what has happened is that we have actually reduced the dimensionality to 3 times 5. So the number of weights now, since the connectivity has been reduced, number of weights is now 3 times 5. Normally what we want to have is that we want to have the type of connections which is much, much smaller than the input. So if you now suddenly have, suppose you have 10,000 input nodes and you have a connectivity of 3 only, that means that we will only have 3 times 10,000 weights. Instead of, suppose you had something like 10,000 hidden nodes, you would have had 10 to the 8th weights to determine. Now suddenly you have reduced the problem down to something like 10,000 times 3, which would be 30,000 instead of 10 to the power of 8. So the whole thing with this filtering is that you're looking often at some adjacent properties. So if the color is the same throughout the house, that means that you don't need to feed in the information about all the pixels which have a brown color. You would just need some few adjacent points. So this is one of the ways you would typically reduce the neural network. Another of the properties is actually something which is called parameter sharing. So that's one of the next things. And that means that in that specific case, you would actually share the same parameters parameters for more than one function. So to understand that, the way you could think of this is that you could have a single parameter which is used in all the input locations, and that reduces the storage need for a specific type of parameters in a hidden layer. And the thing then is that when you have this kind of connectivity, you can actually have through other types of connections, you could then have parameters which would actually, how to say, what's the English word now, which will propagate throughout the network. And you could think of this in the following way. So suppose we have this input nodes, x1, x2, x3, and so on. Now you would have a hidden layer here. And in this specific case, we would have a connectivity now where this goes into this layer, and this is connected this specific way. We have x1, which connects to the midpoint. So we would have a hidden layer, h1, h2, h3, h4, and h5 here. And then we have some new point up here, so which we could call a G1, a G2, a G3, a G4, and a G5, sorry. Now, the way this gets connected is now that H1, so what we are sharing now is when we say parameter sharing, we are now sharing the connectivity. So X1 connects to H1, which then connects directly to G1. The node H2 receives an input from X2, but then it also sends into G1. The next thing which we have now is, so let's just draw this. So we would now have an H1, which also feeds into G2. So it means that even though X1 now sends only to H2 and to H1, when you propagate in the network, it will also affect G2. When I'm sending in from X2 here to H2, that goes into G2, but it also propagates into G3. So when you make the network deeper and deeper, the information which is encoded in, let's say, X1, X2, X3, can actually propagate to many of the output nodes. So the same thing happens here. So we would have an X4, which connects with H4, which goes straight to G4. So with parameter sharing, it means that we have X4 goes directly into H4, goes directly into G4. But then there is also some kind of propagation of the connectivity in the sense that this node here also sends information to G3. It sends information to G5. Similarly, what we see here is that the information which is sent from X3 is also sent into H4, which then propagates to G4. So even though X3 links directly with H3 and which links directly with G3, so that's the way we now are setting up the connections. We get back information from the different nodes at a later stage. So that means that the direct connections are sparse. However, what you have then is that the units can be in a deep layer. They can be indirectly connected to all or most of the inputs. So let's just rewrite that one. So we have direct connections. And this limits the number of connections are sparse. In our case, we actually chose only 3 connections from one node. However, what you have is that units can be connected to each other. So units can be in deep layers. They can actually be connected to all or most of the units in the input layer, or in our case, this would be the input image. So the direct connections are sparse. However, units can be in deep layers connected to many, if not all, or all of the units in the input image. Normally, this kind of convolutional layer, which we have inside this convolutional stage, that can contain several filter operations. So we are not limited to only one type of filter operations. When you're done with this type of operations, you would then send like this G1 and G2, G3 and G4 and G5. That would be massaged through a filter, no, an activation function. And then when the activation function has produced this output, it then sends in the next stage into something which we call a pooling layer, where you can reduce the dimensionality further. And let's see how this pooling layer now affects the dimensionality of the problem. So we have a convolutional stage which can contain several filters. So the design which we have here with H1 and G and 1 and G2 and so on, these could now represent a chain of filters which is set up in the convolutional part of this convolutional layer. So this output goes into a activation function, goes into and keep in mind now that these kind of filters, they are really handcrafted to the specific problem. That's been the strength of convolutional neural networks, that if you have specific images you want to train your network on, you can really handcraft the type of images you want to reproduce so that you can really perfect the recognition of, let's say, human faces, or a recognition of a specific type of tumors. So convolutional neural networks have been extremely successful in medical imaging. So this goes into an activation function. So let me just correct that writing a little bit, into an activation function. So this is normally called the detection stage. So then after that, we have the final process, which is called the pooling stage. And let's take a look at what that actually means. So we can have, as I said, several convolutions in parallel with different filters. Then we send things through the pooling. And there's something which now is normally done in the pooling staging, which is called max pooling. But what this pooling function does, or pooling stage, pooling, that replaces the output at a certain location, which means at a certain node, at a certain location. So read this as node in the pooling stage or the pooling layer with a summary statistics. Summary statistics of the neighboring points of the nearby outputs. Summary statistics of the nearby points. And the most common way of doing this is something which is called max pooling. That's the most common approach. So let's just illustrate what max pooling means. So max pooling is a process which is extremely simple. So suppose now that we have some, after we've gone through these operations, we have now 5, or let's just take 4 just for the sake of simplicity. And we have a connectivity of 3. So this is also a parameter which we have to decide upon. And now we have the outputs here. So the connectivity is 3. So this connects with this one. This connects with that. This connects here. This connects here. It connects with that one. This one connects with only the 3 outputs. And let's now suppose that after the detection stage, this specific node here, let's call this an H1, an H2, H3, and H4. They have a specific value. So this could have a value of 0.1. This could have a value of 1. This can have a value of 0.2. And the final one has a value of 0.1. So these are the values which you would have gotten after you have run through everything in an activation function. So this is the output of activation function. Now, max pooling simply says now that you pick the max value. So this one would feed in to this node here, G1, G2, G3, and G4. So this feeds in 0.1, and then it also feeds in 2, and we simply pick the maximum value. So that means that the output here, if we now look at that one, that is going to be 1. So this is the largest value of 0.1 and 1. It means that the output from G2 is going to be 1. The output from G3 is going to be 1. And then finally, the output from G4 is going to be the maximum value of 0.2 and 0.1. So this is simply going to be 0.2. That means that we can reduce further the dimensionality. So in this specific case, we have 3 values which have the same value. So we could now say that we reduce this one to just 1 output node, which carries a value of 1. And then we would typically continue along the line here. So we would have many more connectivities. But in general, if you have decided on this kind of sparse connectivity, you would then typically affect only 3 output nodes from a given input node. And you simply keep the maximum value. So that's pretty simple here. And this is basically what is done when you're dealing with max pooling. And in that case, you have and it depends also on the stride you have chosen to have. But in this case, what happens now is that you would reduce the dimensionality here from 3 down to 1. So this is actually a further downsizing of the final output from a convolutional process. So you have done a reduction through a filtering, and you can apply many filters in parallel on the data. Then, when you're done with that, you run through a detection stage. You produce an output, which is what we plugged in here. And then, based upon that, we simply pick the largest values, and that would reduce further the dimensionality of the problem here. So these are the basic elements of a convolutional neural network. And these are parameters which you would need to tune in order to find the best possible representation of your data. So what I'm going to do now is actually to go back to the way we can set up a neural network, a convolution neural network, using, for instance, Tensorflow. So the basic operations are those which we have described here. If we now go back to the slides, so let's try to do that. And look at a specific example and how we would program the convolution neural network. So the convolution neural networks are often built from the assumption that the inputs to the network are typical images. They could be two-dimensional images, but they could also be three-dimensional images. And the basic operations, as we've been saying, is a convolutional stage and a pooling layer together with this detection stage. And you would have to define your data in terms of the inputs, the pixel width, the pixel height, and then the depth. So the depth will typically be represented by the number of colors which you have. So if you have now the Eminence Data Set, actually the original data set, it contains handwritten numbers with 28 times 28 pixels. This is a pretty blurred data set already. What we did when we used the scikit-learn data set for the Eminence numbers, handwritten numbers, we actually went down to 8 times 8. Sorry for this. So if we were to analyze an image of a size 128 times 128, we would actually have to have 16,000 weights to each neuron. And even worse, if you were dealing with color images, as most images are, we would actually, in this specific case, we would have something like 49,000. Now, for the Eminence data set, what we typically end up doing then is that we end up using this 8 times 8. And if we now look at it, these are things which we have discussed. I'm actually going back to the Jupyter notebook here, but we can look at what we are doing first. So I'm inputting the data set, which are now these handwritten digits. So this is a very much downscaled data set. And it contains now images which have 8 times 8 pixels. These are gray images. And if we go back to the Jupyter notebook here, so let me just reconnect here. Just go up a little bit. I just need to go back. So I've been using Google's Colab when I've been running this calculation here. So the Eminence data set, which we have been looking at, contains these handwritten numbers, and the specific data set contains of a width of 8 pixels and a height of 8 pixels. The depth is equal to 1. And you can see here the numbers are not very, the quality of the images are not impressive. These are all labeled, and some of these numbers, if you as a human, are difficult to recognize, but with some goodwill you could say that this is a number 3, this is a number 7, and this is a number 8. Then we can now use Tensorflow, and if you look at Tensorflow, the way you would import it now is to import and it's very convenient to use Keras as an API connected with Tensorflow. So I'm introducing the layers and all the different parameters which I need. So I'm having the input layer, and this is a sequential process. I want to have a dense neural network. I'm inputting the type of optimizers. I'm inputting the type of regularization I want to apply, whether it's an L1 or L2, other types of optimization or regularizations. The optimizers relate to the type of gradient method I want to use. And this is typically a stochastic gradient descent variant, like Adam or RMS prop, or just a plain stochastic gradient descent. Then we do the standard train test split, which we have always done, splitting the data into 80% training and 80% test. Then, when we run this with Keras, what I've done here is simply to set up my own function. And now I'm putting up layers here. And you can actually define the size of the layers which you want to output. So in this case, I'm setting up a layers, the convolution 2 dimensions. I define the number of filters, the type of receptive field, the input shape. There's something which is called a padding, which also has the same thing as a stride. I define the activation function, which now in this case is relo, and I can also add a regularization parameter. Then I can add a pooling layer where I can define the pooling size. You can flatten this. So this means the flatten means just you taking the output from the pooling layer, and then you would simply just, so this flattens input, does not affect the batch size. So it means the flattening means that you transform what you had as a matrix into one-dimensional vector. You can add layers, and one of the things you can do then, if you look at this now, you could simply add a simple feed-forward neural network if you want to. And then at the end, you have the output layer where you have to define the number of categories. In this case, it's 10. You define the kind of activation function, which in this case is a softmax function. You can also have a regularization term there. So these become all parameters here. And then you can also define the type of type of loss function which you want to deal with, and the type of metrics. And in our case, we're just looking at the accuracy. And I'm setting up the data, input size and everything. I'm running this over different values of the learning rate and different values of this regularization parameters in an L2 regularization. And then I'm simply setting up I'm calling my neural network, which is now set up with a convolution stage or convolution layer, which does the filtering, the detection stage, and then it produces a via pooling layer, produces an output, which is then fed into a standard feed-forward neural network. You can actually make these layers deeper and deeper and deeper. And here, the metrics I'm interested in is now simply the accuracy. So I'm simply counting the number of results which have been correctly reproduced. So in this specific case, when I run my network now, if we scroll down a little bit here, we can just view the image of it. So I'm just running through this, all the data which I produced from my convolutional neural network. I'm running that through the display with the seaborn. And in this case, you can see now for the training, this is the training data. And you will see now that for a learning rate between 10 to the minus 3 and 10 to the minus 2, I get results which are not that different from a standard feed-forward neural network. Actually, for this very, very reduced type of images, a standard feed-forward neural network does an equally good or perhaps an even better job than the convolutional neural network which I put up here. Remember also that the data set is pretty small, so we don't have that many parameters here to determine. And in that sense, perhaps just a plain feed-forward neural network with one hidden layer does a job for us. And if you look at the test accuracy, this is basically at the same level as we had previously with a standard feed-forward neural network. Remember that the human detection capability for these handwritten numbers, which are pretty blurred, is something like 98%. So our feed-forward neural network with a convolutional layer is actually doing a better job than an average human in recognizing these images. So for the hyperparameters of lambda, which is 10 to the minus 4 here, and then the learning rate, which is 10 to the minus 3, we are actually getting an accuracy which is 99%, which is not so bad for this specific data set. Now, there are other examples here there is one data set here which contains now something like 60,000 color images in 10 different classes. And in this example here, which you can find in the Jupyter Notebook, the data set is divided into 50,000 training images and 10,000 testing images. And you can set up a similar neural network here. You can train the data, you can visualize the data, and you can set up the model. So in this specific case, you could actually decide that you have a convolutional layer, you have your max pooling layer, you can add a new convolutional layer if you want to, you can have a max pooling layer, so this becomes parameters. And one of the things which is nice with the TensorFlow is that you can actually set up a model summary which tells you how many parameters you have. So remember now that your pooling layer does not have any parameters, and you can see now you have the parameters here. The first convolutional stage has something like 896 parameters. The second convolutional stage has something like 18,000, and the final one has something like 36,000. So this gives you the number of parameters, and these are the trainable parameters in the model. And then you have non-trainable parameters, which now are defined by your pooling layer here. And the pooling layer, you will simply then define the size of the pooling layer which you want to deal with. And then you can run the neural network and see how well the model which you have set up. So the model which you have set up contains now a series of convolutional stages. You could have decided to have a less deep convolutional process and just have one convolutional layer with the filtering, which is normally called a convolution, the detection stage and the pooling stage. Then you would flatten your data and feed that one in to a conventional feed-forward neural network. That could have been another possibility. So the thing is that when you're dealing with convolutional neural networks, as you did with the feed-forward neural network, there is a lot of trial and error in order to find the optimal network which does the best possible job in reproducing the data. So the best optimal network then defines your model. Now the algorithm you apply is that of deep learning, convolutional neural networks, combined with the standard feed-forward neural network. And then you would use back propagation in the convolutional stage and in the feed-forward and back propagation stage of a standard feed-forward neural network. But the architecture of the network is what defines your model for reproducing the data which you have. So this is in essence how a convolutional neural network is set up. I invite you to take a look at the textbook of Goodfellow et al. That has many more discussions than those which I presented to you here. So my hope is that this gives you the overarching idea and the overarching understanding of a convolutional neural network and how you can set it up using, for instance, TensorFlow combined with the API Keras. I've been running these calculations on Google's Colab because then it's normally much easier to set up TensorFlow, because sometimes depending on your architectures, if you're running on a Mac with the new M1 processor, for instance, TensorFlow doesn't work very well. And it still actually doesn't work well because it's been tailored to other types of processors. Okay, I'm going to stop here